All right, today we're going to talk about densities of gases, some other derivations that we can get from the ideal gas equation that help us to calculate molar mass and density, because there's questions like that, and I think you should remember this from last year as well. And then we're going to move into talking about partial pressures and some of the things that go along with that, collecting the gas over water, that sort of thing. And this will prepare us for the first lab that we're going to do in this unit, which is going to be collecting hydrogen gas from the reaction of magnesium and hydrochloric acid. So we're going to move pretty fast through this. This is not especially easy stuff. This is actually where the bulk of your AP questions are going to come from. Because there's some gas stoichiometry mixed in here as well. Having chemical equations, doing a little stoichiometry with mole ratios, and then using that mole ratio to figure out, to plug it back into PV equals nRT, and that sort of thing. So this is one to pay attention to. It's going to be a little bit longer. But if you get this one, you're really probably going to get the bulk of the type of questions you're going to see on the AP exam over gases. So, just doing a little derivation here, and there are different ways to do this, okay? But if we rearrange the PV equals nRT equation, essentially what we're doing here, get PV equals nRT, we're dividing both sides by the volume, so then you end up with P equals nRT over V, and then we're dividing both sides by the R and the T, so we end up with P over RT equals N over V. So essentially we're multiplying this by 1 over R times T on both sides, if that makes sense. Just going to cancel out the RT here. So that's how we end up with what they have there. Now the reason that we might want to think about this, this right here, N over V, is because we can remember something about N here. If we want to know the molar mass of something, the molar mass of something is the number of moles, which is N, over that backwards, grams per mole, right? So molar mass is grams per mole, so mass divided by moles, okay? That gives you the molar mass. And then if you rearrange that, multiply both sides by N here, and you end up with this. And then what you can do is you can essentially substitute this in and what they do here, that you've got your, see, this is skipping some steps, trying to make sure this all makes sense. We've got P over RT equals N over V, okay? If we multiply both sides by the molecular mass, so we're multiplying this side by M, and we're also multiplying this side by M, but again, remembering that, well, okay, so we're multiplying this side by M also. Just do it like that. And then this N times M right here, we just said is the same thing as just mass, okay? So if we take the moles times the molar mass, or the molecular mass, this right here, molecular mass, same thing as molar mass, okay? So then if we have this N times M, which is equal to lowercase m, then what we end up with here is M over V equals P times pressure times the molecular mass, or the molar mass, over RT. And the reason that this might come in handy is because M over V is density, okay? Now, this equation, the way we have it written right here, we can actually rearrange this equation, and sometimes this comes in handy depending on what they're asking for. MRT over PV, okay? So if we have that rearrangement of these things, and I think that's right. Yeah, that's right. So the nice thing about this is if we're given a mass and we're asked for a molar mass, then this is a way that we can solve this for this gas. Now again, these are just equations for gases, so we can only use them then. The way that we remembered this last year in my class is molar mass right here. To solve for molar mass, it's Mr. T poops violently. Mr. T poops violently. Kind of gross, but it'll stick in your head. So that can help you with that one if you don't want to worry about deriving it every time. Mr. T poops violently, that'll give you the equation. Now, like we said, density is mass divided by volume, so you can actually substitute density in here. Okay, and actually this is, I don't know why they made it a lowercase d. So PM over RT. Okay, and again, another way to write that equation that might help you remember it a little bit better. Molar mass equals dRT over P. Okay, and the way you can remember this one is that Dr. T poops. Okay, so Mr. T poops violently. Dr. T, you know, he's grown up a little bit, he's gotten his doctorate, now he just poops. Okay, so again, kind of weird, but it will help you remember it. Okay, and that will get you the molar mass equation when we're given the mass and the volume. That will also give you the molar mass equation when we're dealing with density instead. If you want to solve for the density, you just rearrange this equation here until you get this. Okay? So what that means is you may be asked the density often on the AP exam. And the thing to notice here, okay, this is kind of useful. All other things being equal, if you look at the fact D and M are both on the top of their respective equations, and so I guess it doesn't do any good to rewrite this, but if you remember this from yesterday, when two things are on opposite sides of the equal sign, that means they're directly related. Okay, so as the molar mass increases, the density of a gas should also increase. Okay, and so if they ever ask you a question about which of these gases has the highest density, if that's a question on the AP exam, you pick the one with the highest molar mass. So it's fairly simple. But all of the things being equal, pressure, temperature, all of that being equal for two gases, you're going to pick the one with the higher molar mass. That's the one that's going to have the higher density. Okay? Okay, and actually this is a rewriting of what I showed you on the last slide. Dr. T poops. Okay? So again, the two equations that you'd probably want to remember for the that involve molar mass: Mr. T poops violently and Dr. T poops. If you remember those two, then you should be fine. Okay, so question here: what is the density of carbon tetrachloride vapor at 714 torr and 125 degrees Celsius? All right, so on this one, this is a density question, and it might not seem at first like they've given us the molar mass, but they have, because they gave us the name of the compound, so we can figure out the molar mass. So molar mass equals Dr. T poops. That's the one we need to use because that's the one that has density in it. Okay, because they're asking us about the density. So one of two ways you can solve for this. You can either solve for density first, and then plug in all your numbers, or you can plug in your numbers first and then solve for D. And traditionally, students seem to be more comfortable with plugging in numbers first and then solving algebraically after that. So we'll do that. If it makes sense to you to do it the other way, to rearrange the equation first, then do that and then plug everything in. That's actually my preference because I think it's a little bit cleaner, but we'll do it this way because students seem to prefer this. So carbon tetrachloride, first thing we got to remember is what that is, and that should be fairly easy. That's a covalent compound. They're giving us prefixes, so that's just going to be CCl4. And the molar mass of CCl4 is going to be, I'm going to approximate a little bit here, 35.45 times 4 plus 12 for carbon, so 153.8 grams per mole is our molar mass there. Okay, so we'll just plug everything in here. 153.8 equals D, that's what we're trying to find, times R. Now this is a little tricky. We have to watch our units here, okay? Because the R that we typically use is for atmospheres, and it's probably easier if you just, since you're not going to have the equation sheet, it's probably easier if you just memorize one number for R, and that's the number in atmospheres. So we'll do that, and we'll convert this pressure to atmospheres here. So 0.08206. And again, the units there, liters times atmospheres over moles times Kelvin. We'll see if all these units work out here. And then we're going to multiply that by the temperature, which has to be in Kelvin. So that's 398 K. And then we're going to divide that by the pressure, which the pressure is 714 torr. To get 714 torr into atmospheres, we just remember there are 760 torrs in one atmosphere. So you take 714 divided by 760, and that'll give us about 0.939 ppm. Okay, and that's what we can plug in down here. That way we make sure we have the same units on these things. You just have to be really careful with that. Pay attention to what R you're using and what your units of pressure are. Okay? So then we just solve this thing using cross multiplication. Not really cross multiplication, but we'd multiply both sides by the 0.939 to get rid of that fraction. And so once we do that, we end up with 144 point, and I won't round until the end here. This is grams per mole. I guess it's technically grams times atmospheres per mole, which is a strange unit, but I'm trying to keep track of my units here so that I can show you something, okay? And that's equal to all this other stuff, D times 0.08206, liters times atmospheres, over moles times Kelvin, times 398 K. Now when we multiply these two things together here, and then divide everything by that, let's see here, 0.08206 times 398, gives us 32.65. So what we're going to end up dividing this side by is 32.65988. And again, we'll round at the end here. And when we multiply these together, the kelvins cancel out. So what I'm left with here is liters times atmospheres over moles. Okay, so the things that are going to cancel out, atmospheres, moles, moles. So notice the units we end up with here for our density. You have to be a little careful on this, because typically we'd have grams per milliliter or grams per centimeter cubed or something like that when we're dealing with density, but on these, our units are grams and liters. Okay, so this is going to be grams per liter for our answer. So when we figure this out, we're going to get about 4.42 grams per liter for our density. Okay, and anytime that you're using the ideal gas equation or derivation of the ideal gas equation to solve this problem, you're going to end up with grams per liter as your density. Okay. All right, next. Series of measurements are made in order to determine the molar mass of an unknown gas. Large flask is evacuated and found to weigh 134.567, then filled with the gas, and now its mass is 137.456. So that's indirectly giving us the mass of the gas, right? It's saying when it's completely empty, here's the mass. When we have the gas in it, here's the mass. So we subtract those two, that should give us the mass of the gas. And the pressure is 735 torr, and it's 31 degrees Celsius. And then it says the flask is filled with water. Thrown away 1,067.9 grams, and the density of the water is... they're not making this easy on us. So, we're trying to calculate the molar mass of the unknown gas, and we know the mass of this gas, but we don't know its density or anything like that. Okay, we know the density of the water, but we don't know the density of the gas. So probably the best equation to use for this one is Mr. T poops violently, because we are given a mass, but not a density. Okay? So anytime you have a density given to you in the problem, or if it's asking you for density, it's probably best to use Dr. T poops, but on this type of equation or problem, you're going to want to just use Mr. T poops violently. Now the problem here that you might see is we've got an M, we've got a T, we've got a P, but it's not immediately apparent that we have a V. Okay? But here's the deal. After we figure out the mass of the gas when it completely fills the flask, then we fill this flask with water, okay? And we know the mass of the water. Well, okay, I take that back. We know the mass of the water plus the flask, okay? So we take the 1,067.9 minus the original mass of the flask. That would give us the mass of the water. And we know the density of the water. So knowing those two things, we can actually find the volume of the water that filled up this flask, okay? And that essentially gives us the volume of the flask, okay? Which means that's also going to be the volume of our gas. So that's pretty tricky. They could throw something like that at you on the AP exam. So the way we'd go ahead and solve this one, we got this 1,067.9 grams of water, and we're going to subtract the 134.567 grams of the flask, and that's going to give us the mass of the water. $933.333. I think I did that right. That's grams of H2O, and we know the density of the water. And so the density of the water here is 0.997 grams in 1 milliliter. And while we're at it, let's go ahead and convert this to liters, because when we plug into our ideal gas equation, we've got to have this in liters. So 1,000 milliliters in a liter. So then we divide this by 0.997 divided by 1,000. So we have 0.936, 3 sig figs here, liters. Okay? And now it's just a matter, once we have that figured out, it's just a matter of plugging into the equation. Okay? And again, 0.936 liters, that's telling us the volume of the flask, because when we completely filled this thing with water, that was the volume of the water. Okay? And so we can assume that that's also going to be the volume of a gas when the flask is completely filled with the gas. Okay? So we've got molar mass is equal to M. Now our mass on this one, we're going to have to take the 137.456 minus the initial mass of the flask. .889 grams times, again, we're going to have to do our R, and I prefer to use the 0.08206. I'm not going to be as much of a stickler about units on this one because I kind of showed you what I wanted to on the last one. 31 plus 273 gives us 304 Kelvin for our temperature. We divide that by the pressure, which again, we're going to have to take 735 torr, since I used the R that's in atmospheres, and we're going to have to convert that. really, you can probably remember that what you need to do on these is divide by 760. 735 divided by 760, 0.967 atmospheres times our volume, which we found to be 0.936 liters. And that should give us our molar mass once we figure all that out. One calculation. Our molar mass should be somewhere around 79.6. Now my rounding may not have been great on that one because I was hurrying a little bit, but our units here are going to end up being grams per mole because those are the units for molar mass. And there it is. Okay, hopefully that makes sense. Now, there are also going to be stoichiometry problems when we're talking about gases here. This is one example of the type of stoichiometry problem you might see. And really, this is not that complicated. All it is adding one additional step usually to either the front end or the back end of your stoichiometry, okay? And so we've got this problem here. We've got the airbags, and this is actually the reaction that takes place when an airbag fills with a nitrogen gas in your car. And I mean, it's pretty impressive this reaction happens that fast, that it can actually fill up with gas fast enough to stop your face from hitting your steering wheel. This is the reaction that's happening there. But obviously, it's very important to do the correct calculations with these to know how much of the sodium azide NaN3 you need in order to not overfill or underfill the bag. And so stoichiometry becomes very important at this point. But we want to pay attention to the volume of the bag, right? Because we're filling it with a gas, so we want to make sure that we fill it with the correct volume of gas. So we know the airbag needs to have a volume of 36 liters, okay? And we know the pressure needs to be about 1.15 atmospheres, and we know what our temperature is going to be. So we need to figure out how many grams of the NaN3 do we need to use in order to make all of that happen, okay? So we've got a volume, we've got a pressure, we've got a temperature, and they're asking us for grams, okay? So one of two things would work here, okay? You can kind of decide what you want to do. We could use, well, okay, you know what? I'm going to say that probably the best way to do this is just to go to moles, because we are doing a stoichiometry here, and we've got to kind of pay attention to this, okay? So our first piece of strategy here on something like this, we want to basically figure out how many moles of N2 do we have, okay? Because that's the information they're giving us. They're giving us the volume of the nitrogen gas, the pressure of the nitrogen gas, and the temperature, okay? But what they're asking us for ultimately is the NaN3, how many grams of that. So we're going to go to moles of N2 first, and then use stoichiometry to get the rest of this done, okay? So the first part of this problem, we want to do PV equals nRT. And so the pressure here, 1.15 atmospheres. It's kind of nice. Finally, we have 1 atmosphere, so we don't have to convert it. Times volume, which is 36 liters. That's equal to N. That's what we're trying to find. Times the 0.08206. Times our temperature, which is 299. And then we're just going to solve for N here. Okay, so our N is going to be 0.593 or something along those lines. Actually, I guess it would be just 59. But I'm not going to round it quite yet because we're going to do some other calculations here. That's moles of N2. Okay, that's what we just found because this is the volume of N2. This is the pressure of the N2. So that's what we're finding is moles of N2. All right. So then we're going to take this, 0.593 moles of N2, and then once we have this, we can just do stoichiometry with it. Okay. Remember that the goal in any stoichiometry problem is just to get to moles. Okay, and sometimes you can use PV equals nRT to do that. So we've got 0.593 moles of the N2, and we want to go from moles of N2 to moles of NaN3, because that's what they're ultimately asking us about here. NaN3. 2 moles of NaN3 for every 3 moles of N2, according to the equation. And then we're going to go from moles of NaN3 to grams of NaN3. And I have to do some molar mass here. I'm going to be a little bit approximate here. Sodium's about 23, and so nitrogen's about 14. There's 3 of those, so we're talking about 65 grams here in 1 mole. So we're going to take the 0.593 times 2 divided by 3 times 65. And that should give us a mass of about 25. I guess we can only be precise to the second significant figure here, so 26 grams of NaN3. And I'm sure they are more precise than that when they actually do the airbag calculation, but that's about how many grams of the sodium azide we'd need to make sure that this bag inflates to 36 liters, okay? Assuming this reaction all goes to completion. So that's an example of the kind of stoichiometry problem you might do here. All right, moving on. Dalton's law of partial pressures. This is a pretty simple thing. This basically says that if you have a bunch of different gases, you add up all of their partial pressures, and that gives you the total pressure. Okay, nice and simple. Okay, and that's about as far as we got with that last year. So essentially, you might see a problem like this. This would be nice and easy if you saw something like this. Okay, gaseous mixture made from 6 grams of O2 and 9 grams of CH4. And we want to know what is the partial pressure of each gas and what is the total pressure in the vessel. I say nice and simple. This one actually is not entirely simple because they're not giving us the pressures here. They're giving us masses, and they're giving us volumes and temperatures. Okay, so guess what we have to do? PV equals nRT twice. Okay, except we don't have an N right now. We don't have the number of moles. What we have is the number of grams. So before we do anything else, we have to figure out how many moles of each of these we have. So we've got 6.0 grams of O2. And this is going to be 32 approximately. Again, I'm just approximating here. 0.1875 moles of O2. And then same thing with the CH4. 0.0 grams of CH4. This video is going to be long. And then we just take that divided by 16 and 0.5625. Okay, so now we have the moles of each of these. And essentially what we're going to do here is plug into PV equals nRT for each of these. And then we're going to figure out what each of the pressures are, and then we add them together to figure out the total pressure. Okay, so PV equals nRT twice. Now, there's another way to do this, but we haven't really talked about the mole fraction yet, so we'll just do it this way. So when I plug into PV equals nRT, I'm going to do this without really showing it. Hopefully you get the idea of how to plug into this now, and we're just going to solve for the pressure. Pressure is equal to nRT over V. Okay, so you just take the number of moles of each of those, multiply by the temperature, divide by the volume, and that should give you the right answer. And this pressure is going to be in atmospheres, which is fine. It doesn't specify, so we'll calculate it in atmospheres, so we don't have to do any conversions. So the pressure of the oxygen here is going to be 0.1875 moles times 0.08206 times our temperature, which is going to be 273 because it's at 0 Celsius. And then we're going to divide that by the volume, which is 15 liters. So our pressure for oxygen is going to be 0.28. These are all 3 sig figs, it looks like, so 0.280 atmospheres. Okay, and then the pressure of our CH4 here, we plug that in, 0.5625 times 0.08206 times 273 divided by 15. We should get 0.840 atmospheres. Okay, so there's our two pressures, and then if we want to know the total pressure, we just add those together. 0.280 plus 0.840. That gives us 1.12 atmospheres for our total. Okay, so there's our 3 answers right there. Okay, now we need to talk about mole fractions, okay? Whoops. What happened here? That's very strange. Well, that's unfortunate. Okay, let me take a look at your notes here. Well, here, probably just need to pause this thing for a second and fix that. Okay, sorry about that. I'm having a formatting issue that I'm not able to figure out right now. It has to do with, I saved it as a 97 to 2003 PowerPoint, which I shouldn't have done. And I tried to use an equation thing with it. So anyway, let me just show it to you on the note sheet, what you need to fill in here. So when it says mole fraction here, we're talking about N1 over N total, or that could be a lowercase t, it doesn't matter. So basically the moles of one thing divided by the total number of moles. Okay, now this is sometimes represented by that's called a chi. Okay, it's just a Greek letter that looks like an X, and that's the symbol for the mole fraction of that particular thing. Okay, and it's related to pressure by the following equation. So N1 over NT is equal to the pressure fraction, essentially, so pressure 1 over the total pressure, which is equal to, again, the x1. Okay, you don't have to even curve your x, you can just make a normal x there. Okay, so then if we rearrange this part of the equation right here, what we get is, if we want to know the partial pressure of one of the gases, we can multiply the mole fraction of that gas times the total pressure, okay, and that will end up giving us the partial pressure. Okay, so let me just show you an example of what that would look like, because I think everything else in my notes here is okay. So an example of something like this: study the effects of certain gases on plant growth, required a synthetic atmosphere, and they're giving you mole percentages here of 3 different gases, and they want to know the partial pressure of the O2 in the mixture if the total pressure is 745 torr. Okay, so here's the deal: they're giving us mole percentages right now. Okay, and just like normal, when you have a percentage, if you want to find the decimal or the fraction, then you just divide that by 100. Okay, because what it's telling you is if we have 18% O2, then that's 0.18 for the mole fraction. Okay, 18 divided by 100 here. So if we want to know the pressure of the O2, then we need to take the mole fraction of the O2 times the total pressure, and that would give us the pressure of just the O2, the partial pressure of the O2. Okay? So the mole fraction of the O2 is just 18 divided by 100, so that's 0.18. And mole fractions are unitless numbers, okay? Because if you think about it, if you got N1 over N total, this is some number of moles divided by some number of moles, and that's going to cancel out, so it leaves us with no units. So this is just a unitless number here. So 0.18 times our total pressure, which is 745 torr. And that's going to give us the partial pressure of the oxygen. 134.1. And actually, I guess to be entirely accurate here, we probably would want to just use 3 sig figs on that one. And this would actually be 0.180 when I divide that by 100 to keep my 3 sig figs. So it should be just 134 torr. Okay, second question here. If this atmosphere is to be held in a 120 liter space at 295 K, how many moles of O2 are needed? Alright, so in this last one, we just figured out that the oxygen, the pressure of the oxygen is 134 torr. Okay? In order to have that pressure of oxygen, they're asking us how many moles do we need? We've got 120 liters, and they're telling us what the temperature is. So this is just, at this point, it's just a simple PV equals nRT. Okay? And we're solving for N. So our pressure here is 134 torr, but again, we've got to convert that into atmospheres, so we're going to divide this by 760, and that's going to give us atmospheres. It's 0.176 atmospheres. And that sounds about right, because this pressure, this O2 is just 18% of the total pressure, so it's going to be low. Our volume here is 120 liters. That's equal to our number of moles, which we're trying to find, times 0.08206, times our temperature, which is 295. Alright, solve all of this. Should get number of moles to be about 0.87. I guess it's just going to be 87 because of our volume. So there's our number of moles for that. Okay. And one last thing we need to talk about here, and I know this is just ridiculously long, and I'm sorry about that, but again, this is the big bulk of this unit right here. We're going to spend a lot of time with practice problems that have to do with this. So collecting gases over water. Water evaporates. Everybody knows that, okay? When that water evaporates, you have water as a gas, and that gas has a pressure, because all gases have pressures. So when we're collecting gases over water, like we're going to do in our experiment on Thursday, we're collecting hydrogen gas over water. So the hydrogen gas is going to bubble out of the water. Then we have to take into account the fact that there's going to be a little bit of water pressure also, okay? And the vapor pressure of water is going to be given to you based on the temperature. Okay, so here's the idea of what we're doing. And we did this last year as well. You're going to bubble, you're going to do a reaction that's hooked to a tube. So the reaction is taking place over here somewhere. And that gas is going to be bubbled into a water bath, and it's going to be trapped in an upside down test tube. Okay, those bubbles are going to travel up through this thing until this tube is filled with gas, okay? When you get the water level, the liquid level equal in the water bath and in the test tube, then the pressure in here is equal to the atmospheric pressure outside, okay? The water levels have to be equal in order for that to occur, okay? And so once you have that, then you can do this calculation, okay? So here's an example of the type of calculation you might do with this. Sample of KClO3 is partially decomposed, which produces O2 gas. The volume of the O2 gas, okay, so it's telling us some things here about it. And it's telling us the vapor pressure of the water at 26, okay? So, what we need to know here, we need to know how many moles of the O2 gas are collected, okay? And so, we are given the volume of the O2 gas that's collected. We are given the total pressure, okay, and here's where you have to be careful. This is total pressure. And we are also given the temperature, okay? And so this looks like a PV equals nRT to me. The only trick on this one is we need to subtract from that total pressure, we need to subtract the water pressure, okay? And that will give us the pressure of just the O2, because in that, you know, just like we had in the picture over here, we have two gases in here. We have O2 in here, and we also have H2O gas. Okay, so we have to take that into account when we're considering our calculation here. So 765 torr minus the vapor pressure of water, which is 25 torr. And that, in any problem that you have on the AP exams, that's going to be given to you, because you can't know that water vapor pressure. It's just different at every single temperature that you have. So that's going to be 740 torr. That's the pressure of the oxygen, okay? And then we can plug this into PV equals nRT and solve it like normal. So PV equals nRT. And again, 740 divided by 760, that'll give us the number of atmospheres here. 0.974 ATM times our volume, which is 0.250 liters. And they're giving us the pressure of just the O2 gas, or sorry, the volume of just the O2 gas here, so that's fine. Trying to find N 08206 times our T, which is 26 plus 273, 299. Okay, when we solve all that, I'm moving pretty fast through this. Hopefully I'm not making mistakes in my math. Our number of moles here should be 0.0099, and we're working with 3 sig figs on all of these, it looks like, so 0.992 moles. I know this looks like 2 sig figs, but when you add 273 to it, you end up with 3 sig figs in there, because you have to round to the ones place. Okay, so that's our number of moles of oxygen gas, 0.992. Now the next question here, how many grams of KClO3 were decomposed? Okay, now they're asking a stoichiometry question, okay? And in order to do this, we have to actually have a balanced chemical equation, which they have not given us, okay? So KClO3 is decomposing, and this is reaching way back to when we were talking at the beginning of the year about how to write the chemical equations. This is a decomposition. This is a specific one that you should hopefully remember. This is going to decompose into KCl plus O2. Okay, when you have a chlorate decomposing, it's going to decompose into a salt and oxygen gas. Okay, then we have to balance this thing. Looks like we're going to need a 2 here, 3 here, and then a 2 here. Okay, so there's our balanced chemical equation. And again, if you don't quite remember that from the beginning of the year, that's okay. But these are the sorts of, these are the types of equations that it would be good to remember. And then we know that we've got 0.00992 moles of O2. They wanted to know grams of KClO3. All right, so now we're just doing a simple stoichiometry thing here. Moles of O2, moles of KClO3, and the mole ratio here is 2 to 3. And we're going to go back to grams of KClO3. Let's see here. Again, I'm going to round a little bit. 39.1 plus 35.45 plus 48 gives us about 122.55 for our molar mass here. And when we multiply all of this together, it should give us 0.81. Okay, once again, it looks like we're working with 3 sig figs here, so 0.810 grams of KClO3. All right, and there it is. And that's very similar to the type of calculation you're going to be making on the lab that we do on Thursday. Okay, whew, that's it. Sorry that took so long. But again, that's kind of the bulk of this unit. There are some other things that we'll talk about, but as far as the calculations, that's the big one. We'll do a lot of practice on that stuff in class.